In this video, I am going to evaluate several integrals using numerical integration and Desmos. So let's get started. The first integral that we want to evaluate is this one right here, the integral from 2 to 8 of 12 log of x over x. And we know what the exact value is because Desmos gives us the exact value. So this is the value that we would get if we actually integrated this function using some technique of integration. We can see the graph over here. We are integrating this curve. Essentially, we're finding the area beneath this curve between x equals 2 and x equals 8. So again, that's the interpretation of evaluating this integral. So first of all, let's just see how this is set up in Desmos. Right here, f of x equals 12 log of x over x is where you have to actually enter the function that is being integrated. So you'll see that that is the same thing as the integrand up here. Then we have the upper and lower bounds. A is equal to 2, b is equal to 8. You can enter these using the sliders, or you can just type in the numbers. Sometimes it's quicker to just type in the numbers. Then n, we have to put in the n value. N in this case is equal to 4. Right now, this Desmos sheet is set up for n equals 4, but that can be changed very easily. And then this is the formula for h, b minus a over n, which then of course is using these three values up here to calculate the value of h right here. So we're going to be looking at the midpoint rule, the trapezoidal rule, and Simpson's rule. Now the purpose of this video is not to explain these rules or to derive these rules. That can be done by reading a textbook, watching other videos, or in a classroom lecture. This video is just how to use these rules to integrate something. So let's take a look at the midpoint rule. So as I already stated, everything on this sheet in Desmos is set up for n equals 4. So I will assume that you have at least looked at these formulas in the textbook and you know a little bit about the formulas, but I will kind of explain the pattern that we see here so that we can expand these formulas. So first of all, the area is equal to the height, and the height is being multiplied by all of this in the parentheses. So you have to make sure that this whole expression is in parentheses. Then within the parentheses, we have the function value of 2a plus h divided by 2, plus the function value of 2a plus 3h divided by 2, plus the function value of 2a plus 5h divided by 2, plus the function value of 2a plus 7h divided by 2. So you will notice that we have 1, 2, 3, 4 different function values of four different terms in this rule. That corresponds to n equals 4 for the midpoint rule. Now, each term is 2a plus 1h, 2a plus 3h, 2a plus 5h, 2a plus 7h, all divided by 2. So if we have to add a term, if we wanted n equals 5, the next term would be the function value of 2a plus 9h divided by 2. The next one would be the function value of 2a plus 11h divided by 2, etc., etc. So in the next example, I'm going to expand the formula for 5 or 6, for n being equal to 5 or 6. And so we can see that we actually have the midpoint rule being evaluated here. So what this formula has done, it has taken this value of h, and it has taken this value of a, and it has evaluated this expression to get 23.1436. The exact value obtained by integrating was 23.0617. So it's pretty close for an approximation. Remember that the midpoint rule, the trapezoidal rule, and Simpson's rule, these numerical techniques are approximations. Now let's take a look at the trapezoidal rule. The trapezoidal rule area is equal to h divided by 2 times all of this in parentheses. We start off with f of a plus 2f of a plus h plus 2f of a plus 2h plus 2f of a plus 3h plus f of a plus 4h. Now the pattern here is that after the first term is always f of a. And we consider that to be n equals 0. That means this term is n equals 1, n equals 2, n equals 3, n equals 4. And so the only difference in each term is a plus 1h, a plus 2h, a plus 3h, a plus 4h. The next term would be f of a plus 5h, then f of a plus 6h, etc. The other thing is, except for the very first and the very last term, every other function value is multiplied by 2. 2 times this, 2 times this, 2 times this. But the last term, it's not being multiplied by 2. So this will be valuable when we want to expand this to n equals 5 or 6 or 7 or 8. Now, Desmos has evaluated using the trapezoidal rule, and we get 22.87. That's a little bit further away from our 23 value that we had for the exact value, 23.06. This was 22.87. Not quite as close as we had with the midpoint rule. Let's open that up again. But still not too bad. It's pretty close. For only having an n equals 4, it's a very good result. Finally, Simpson's rule. A is equal to h divided by 3 times all of this in the parentheses. And once again, just like with the trapezoidal rule, we start with f of a. This could be considered n equals 0, then n equals 1, 2, 3, and 4. And so you can see that there is a pattern here. The second term is 4 times f of a plus h, plus 2 times f of a plus 2h, 4 again times f of a plus 3h, and then no coefficient f of a plus 4h. So each term is successfully one value of h greater, a plus 1h, a plus 2h, a plus 3h, a plus 4h. Now, there is a pattern to the 4s and the 2s. Excluding the first term, f of a, which always has a coefficient of 1, the second term always starts with a coefficient of 4, and then a 2, and then a 4, and a 2, and a 4, and a 2, and a 4, and a 2. It has to end with a 4, and then the last term will always be a 1. So you always have to have an even number with Simpson's rule. You have to have n equals 4, n equals 6, n equals 8, n equals 10, etc., so that you can get the pattern where the first and the last terms are 1s, and then you have a 4, 2, 4, 2, 4 rotating coefficients. Okay, the value for this integral using Simpson's rule is 23.0033. Again, very, very close. So all of these are numerical approximations of the exact value. So let's expand this. I'm going to take the window on the graph and make it a little bit smaller. We don't really need to see the graph anymore. And let's take the midpoint rule and let's expand this. Let's say we want to do 6 rectangles. We have 6, n equals 6. So the first thing I need to do is come up here and change n to 6. That's all I need to do up here at the top. I mean, I can change, in my actual integral problem, I should probably do that too. Oh, I'm sorry, we're not changing the b value. That's staying 8. I'm not changing the bounds of integration, my bad. All I'm doing is changing the value of n. So that means in all 3 of these rules, I need to add some terms. So with the midpoint rule, I'm going to have to add, because this is set up for n equals 4, I want plus f in parentheses, 2a plus, now with the pattern, we want 9h, ending parentheses, divided by 2, ending parentheses, plus f, paren, paren, 2a plus 11h, ending paren, divided by 2, and ending paren. So this is now set up for n equals 6. And the approximation is 23.103, as opposed to the exact value, which was 23.06. To modify the trapezoidal rule, we want to add a plus f paren a plus 5h term plus f of a plus 6h term. Now we also have to adjust the coefficients of 2. We need to multiply this term now by 2, this term by 2, and the last term will have a coefficient of 1. So let's just go through and make sure that this pattern looks good. The first term, f of a, has a coefficient of 1, and then 2, 2, 2, 2, 2, 2 there. And then 1 in the last one. Let's make sure we have these all being properly multiplied there. All right. And we also have, check the patterns, a plus 1h, a plus 2h, a plus 3h, a plus 4h, a plus 5h, a plus 6h. And our value is now 22.97. Finally, to use Simpson's rule, we want to add an f of a plus 5h. So plus f of a plus 5h plus an f of a plus 6h. Now what I like to do is go back and adjust my coefficients. We started with 1, we have a 4, 2, 4. Now this needs to be multiplied by 2. And then this one needs to be multiplied by 4. And then the last term is just going to be a 1. And again, we have a plus 1h, a plus 2h, a plus 3h, 4h, 5h, 6h. So the pattern seems to be good. If you do something wrong with one of these, chances are your value down here is going to be way off from the other ones. So as an example, if I put like FF14H here, now suddenly this is 22.0. That's really not that far off, but anyway, that should be 4H. So this is how you can modify Simpson's rule, the trapezoidal rule, the midpoint rule. And clearly you could expand this to n equals 9, n equals 10, n equals 11, n equals 12. You're probably not going to want to go much further than that. In fact, I really don't think it would be necessary to do this any more than 6 or 8 for the n value. All right, so I believe that is pretty much everything you need to know. What we could do if we wanted to is we can just do a different function up here. So let's just evaluate something a little bit different. Let's just do something like x squared log of x. And let's evaluate that from 2 to 18. See what happens. Now, what we have to do down here is change this to x squared log of x. And my lower bound is 2. My upper bound is now 18. And let's keep this at n equals 6. The actual value of the integral is 4969.9. And so we have 4935 for the midpoint rule, 5039, and 4069. So you can see that these values are a lot farther off from the exact value than the previous problem was. That just depends on the nature of the function that we are dealing with. Okay, some functions you're going to get a much tighter relationship between the numerical values and the actual values, and some you're going to be off by quite a bit. All right, that is it. I hope this was helpful, and we'll see you in class.